Okay, this is going to be the binary tree video. Now we're not gonna start this from scratch. We're gonna take all the code that you've been creating as you follow the videos and use that in the binary tree. Now, the reason for a binary tree, and pretty much the reason for this whole course, is for you to learn how not to do things, such as uh, and when I say not to do things, I'm talking about storing a lot of data, and being able to get that data efficiently and quickly, and also having the data the information so that you can get it in one hunk at a time. So essentially, arrays, their weakness is that you can't just ask for one more element in the array. As for where an array is strong, or is its efficiency, because every piece of memory is in order, or in a block of memory that's in order, and it's easy for you to get to a specific index in the array, because all the information is numerically in order. So it's really fast to get that data from the array, regardless of where it's at in the array. But then you've got that you just can't ask for one more. If you need more than what your array can hold, you have to create a whole nother array, copy everything over, and then add another piece of information. So that's where you got your strength of arrays and your weakness of arrays, which then of course you learned not binary trees, but linked lists. And linked lists, you can always ask for more information or more data to be stored through adding new links. But the thing is if you want to get to the data that's inside the middle of the linked list, you have to go either through all the links starting from the front, or all the links starting from the rear, with your head and your tail pointers. So linked lists for large amounts of data are not practical. So then you get into what we call hash tables. So hash tables are basically array based, and what they do is they store the information based on the value of the information. So you always know where it's at in the array, because you just run an algorithm on some data inside of what you're storing, and come up with a key to put it in that position. And that's kind of like your state data hash table. And JavaScript and a lot of languages use it often for arrays, and that's where you have to put a descriptor of what the array value is, or what's going to be stored into the array, and then of course it'll hash that down to an index of where that data is stored in the array. So hash tables are good, but here's the problem with hash tables. They have the weakness of arrays. You can't just add one more. They are efficient because where you're storing the data is based on the data itself, but hash tables are not good for large amounts of data. So there's nothing really that we have up until this point of computer science. Hash tables used to be the thing. Anybody that can create a hash table that can hold a lot of data was king, and that's the way things pretty much went up until about when Google took over the world. So essentially, what ended up happening is binary trees. So is that there was a website that used to be the king of websites before Google took over, and it was called Alta Vista. So Alta Vista was the king of search engines, and you can probably still go to something of what it used to be, but essentially these guys, I would be on a 56K baud modem and do a search, and I can go grab a cup of coffee, come back, and it was still running through all the data out there that they had stored, that they were searching through, and it would take forever to come back with the result. Well, then Google came in with their implementation of binary trees, and you would hit the keyboard and boom, your search results would come right up just immediately. So we got to call in Alta Vista Hasta La Vista. So binary trees is essentially they're only useful for large amounts of data, and that's the key, is because none of these mechanisms that we've used up until the point of binary trees, such as linked list and hash tables, were able to solve large amounts of data. And another issue with hash tables was the collision problem. Is if you're storing data and your key came back two pieces of different data, but they all keyed to the same index, that's a collision. And how would it? And hash tables often were chosen based on how they handled that collision. So with binary trees, you still are going to be putting information in the tree based on the value of that information or a value inside of that information. But the mechanisms to actually go through the tree and get information out, it actually improves with the more information you have in the tree. So that's why it took over, and basically now we're learning how to store information correctly, because nowadays if you're going to be storing any information, it's most likely going to be lots of information. Now, of course, simple programs and whatnot can use arrays. There's no real reason to use hash tables much unless you've got a specific reason for it. But binary trees, they're pretty much king. And essentially when you make a transfer, if you're going to be going towards electrical engineering or any kind of Bachelor of Science degree, binary trees, as far as electrical engineering, computer science, are what you're going to be studying. So it's important for you to have a good introduction to it, which is what we're going to be doing today, because you will be working with them as you progress. Pretty much binary trees will be your life if you're going to be transitioning into a 4-year university for computer science or electrical engineering. At this point in my own education, I had been introduced to linked lists, mastered linked lists, and been introduced to binary trees, but it took me quite a bit of time before binary trees really sunk in, actually until I had to teach it. So it's really important that you spend the time on understanding this. And what's nice is once you understand linked lists and specifically the implementation of binary tree that we're going to be doing with recursion, you'll be ready for this. So binary trees are pretty much they're the same idea of linked lists with self-referential data, but they, instead of a next and a previous, they have what we call a left and a right. So what we're going to do is we're going to take code that's already created, and that's going to be your phase 1 accounts list starter and binary tree example. There should be a video up here, but I'm creating it right now. So you'll use these two examples for your code today. So what I'm going to do is I'm going to create a new project, and these folders I've got right here, and we're going to just steal some code from these guys. We're not going to create the binary tree from scratch. We are going to be creating it. Well, I think what we'll do is we'll take the linked list that we create and convert it to the binary tree. We'll see. Let's just kind of get going and see what we got. Let's begin with creating a project first, and that we're going to bring this code into. And then we'll go grab some code from those two folders. So I'm going to call this binary tree. And the binary tree we're going to be creating is going to be templated, and you're going to be able to use it to sort or to put numbers, customers, transactions if you want, accounts. But what you'll have to do is, since it's templated, if you're going to be like storing customers in the binary tree, you're going to have to overload the less than or greater than operator inside of your customer object. So I'll kind of allude to that as part of your project, that, or not for your assignment for this chapter, as part of our discussion. Or you can do the alternate assignment that comes from the books, binary tree example. And I just want to give you guys options. A lot of people, they do better with books and with the book example code and reading through it. Other people do better from direct instruction or videos that I give, where I show you a different way of doing things other than the book. So let's go ahead and get started. Let's see, we want our empty project, console based, C++. I think, didn't I? No, I was doing something wrong. Never mind. Okay, so call your project binary tree or whatever you wanted, actually. Okay, so we got our binary tree project created. And what we're going to do is I'm just going to minimize this, and I want to look at what we have in the binary tree example. And it looks like we do the customer.h here. And do we overload the so here, let me allude to this. You've already pretty much got most of your, here's the overloaded operator for the less than and greater than for your assignment. So this is actually a good place to go. So we look at the BTree. The BTree is right here. Here's our node, but we're going to be using the node that we created. So we're going to actually come back and steal this code only. The other stuff we're going to take from the code that I've been putting in the videos for this whole quarter. So we're just going to steal the binary tree code from this. You'll be able to find it there. So what I'm going to do is take this code that is in the phase 1 account starter list, or list starter, and I'm going to go to the stat q sort code, and I'm going to grab this customer. And why not? I'm going to grab the customer list also. I'm going to grab the linked list because we're going to actually use this linked list to create our binary tree. In fact, we're going to separate out the node class also as we do that. I don't need anything else, so I'm just going to take those guys, and I'm going to go to my new project. And again, this binary tree example, we're just gonna grab the code from it for the binary tree, and then what I'm going to do is I'm going to get my trusty graphics tablet out here. I'm pretty sure I'm a lot better than I was at the beginning of the course. And we'll just walk through all the binary tree algorithms, and I'm gonna simplify it as much as possible. But if you do not understand the winding or the unwinding of a stack, and you didn't do the print stars program appropriately, you're gonna have a bit of a difficulty, because you can actually do things as the stack is unwinding. And that's where people have the biggest problem understanding how the recursive or the binary tree implemented recursively works. Now, Google, of course, will not have a binary tree that works recursively, because every time you wind the stack, you're putting more data on the stack. And if you have a big enough tree, you're going to blow the stack. So they would do loop-based implementations of the binary tree. But if you understand the recursive approach to binary trees, you can readily adapt that to a loop so that you don't have the blowing of the stack problem. So I just want to emphasize that this recursive implementation of binary tree is an example, and it's really slick, and it's cool to talk about, but it's not practical, because you would eventually blow the stack by having so many function calls that are being called recursively depending on the size of the tree. So what do we got here? We've got our project. I need to take those files and put it in the project that I just created, which is this guy right here called binary tree. Let's compile it so I can get a folder in here at least. No, I think maybe I could probably put that thing in there. Let's see. Build, rebuild, Okay. Okay. There we go. All right. So that's in our folder, and now we're just going to add it to the project. Add existing item. Select those, and then we're going to go ahead and go to project, add new item, and this one will be our main. Okay, and then we're going to add two more. We're going to add two more, and then do some porting. In fact, actually, we don't need to add. What we can do is we can just rename this to node and get rid of the, because I want this to be the node class, and this is the node that we built. And what I'm going to do is I'm going to get rid of this linked list. This is going to become BTree. So what we're going to need is we can get rid of all of this add code. All this add code for our linked list is going to go away. In fact, we're not going to call this node.h. We're going to call this btree.h. So we're going to rename it again. Okay. Keep the print for now. Okay, so this is going to be, we're going to rename this BTree for our linked list. So let's go over here and rename this BTree. And we're going to keep the node class inside of this. Okay, so this is going to become BTree. And just so you don't get this confused with your linked list code, we're going to call this bnode. Okay, so we renamed the class, the node for a binary tree to bnode, and we rename the linked list to BTree. So here's the other modifications that we need. Obviously, we got to change our constructors, and this has to be taken care of. The get count is good, but here is the binary tree is kind of like an upside down tree, and the first link is what we call the root. So this is going to be renamed to root. Okay, and constructor root equals 0, count equals 0. We do not need a tail. Okay, get counts fine, print, this will be changed. Okay, so that's our class binary tree. The main difference is that we just have a root, and we got to make sure that that root is assigned null right off the bat. Then we go up to node, and here is with node, it's going to be now, it's not going to be next or previous, it's going to be left and right. So we're going to port this. Oh. So that everything that says right that says next is going to turn to right. Because binary trees has a left side and a right side. Okay, and then we're going to have this set previous. Anything that says previous is going to be turned to left. Okay, so this is going to be left, and this is going to be left. This is right, and this is left. Okay. All right, so the left and right is just the same as next and previous, but we're going to be using these differently. So a binary tree, you need to insert the data. You don't want to insert the data in order. So basically, a binary tree is fairly close to the same kind of self-referential mechanism that a linked list has. So this node class is now done. So now we can have binary tree nodes because we have our left and right side and our data is going to be the same. We have our accessors that have been redone. And then our binary tree, we got rid of everything but the constructors and renamed the root node, which is going to act like the head node of your linked list. And then we keep the print function, which is going to eventually be changed. In fact, we probably should just get rid of it. We're not going to need it, just to simplify things even further. Okay, now this is not going to work. There's actually an algorithm that they have for deleting a binary tree that you can put in here. Now this is going to be an introduction to binary trees. You're going to be expected to go in pretty deep with binary trees in some of your coursework that's coming up as a junior and a senior. So spend the time on this and understand it. And of course, if it's after the quarter's over, I'm pretty sure you might have still have access to the videos. Okay, so far we have our customer list type. Actually, you know what? We can get rid of this. Okay, in fact, let's go back to the folder and do some cleaning. Okay, so now we just have the BTree, basically skeleton. The node is completed. The binary node is completed. That's done. And then we're going to eventually store customers in there. So, and this is where you're going to have to overload the less than operator so that you can compare customers as part of your assignment. But I'll let you guys put that together. I did give you a hint on where example code for that was. Okay. All right, I'm going to pause for a second and come back, and we'll begin building this binary tree from the example code. Okay, what we're going to do now is we're going to get the binary tree example code from that folder that I was discussing, this binary tree example, which is right here, and we're just going to steal code from it. So open up btree.h. And we're going to do this with the naming of what you guys have developed through the videos. Now, I'm going to just grab two functions, and that is this one, insert node helper. Now, notice the double pointer here, and I don't get freaked out about that. I'm going to explain that as we progress. Why we have a double pointer, and this is crazy weird code right here also, but that's because of the double pointer. Essentially, we need the pointer for the nodes, or for each node, and we need the double pointer to pass it by reference to the recursive function so that it's not making a pointer or not making a copy of the original pointer. So you need the double pointer because you are passing the original pointer by reference. And that's why you have this ampersand here, because it's getting the address of the initial code, and this dereferences the left side node. So yeah, it's a nightmare bit of code, or to kind of visualize, but it all comes down to those three sides of pointers. So remember, a double pointer is just a pointer to a pointer. And if you want to pass that pointer by reference, then you must do it through a pointer to the pointer. It's like passing a variable by reference. You need a pointer to pass a variable by reference. Well, what if you need to pass a pointer by reference? So you need a pointer to pass a pointer by reference. So that means it's a double pointer, a pointer to a pointer. Versus if you're passing a variable by reference, it's a pointer to a variable. So basically think about that single pointer as just the variable and the other pointer as taking the reference of that variable or pointer, double pointer. So anyway, yeah, I'll get into the why that double pointer needs to happen, but essentially it is because you have to pass the pointer by reference. And that is so that you do not make a copy of it when you pass it to the recursive function. It actually passes the original pointer itself without making a copy. So it does not do a pass by value. It does a pass by reference of the pointer itself. Okay, so this is the main code that we're going to be talking about first. And I'm going to walk you through each bit with the whiteboard here. Now, the reason why we need this insert node helper is because we need to pass the root node first. And that means that, and we don't want to give somebody who's using the binary tree access to this root node. So we put in an insert node function that they use as an accessor to run this recursive function bypassing the root. So this insert node right here, insert, just essentially uses the insert node helper function, which this could be a private function. You can make this function private. And essentially it's so that you can access somebody who's running the insert function can get the recursive call and start it out with the address of the root and send the data that they want to be stored. So we're just going to take these two functions, the insert and the insert node helper, and we're going to walk through that code. And we're going to port it first to our example. So I'm going to minimize this, and we'll come back to this later. That's not our project. Our project is over here. So we're going to go back to, go ahead and close, customer.h. And, main, well, we probably should flesh in main a little bit here. But let's go ahead and copy that code in first. So B node is going to have these functions in it. Insert node, helper, and insert. All right. And what we're going to do is I'm going to be inserting nodes in from main, and I'm going to draw out a map of how this works. And then the next part we're going to be doing a linked list traversal, and that'll probably be the next video. That'll probably be part 2. We'll start with the insert node. Usually it takes about 2 hours of commentary to kind of thoroughly go through the binary tree. So we'll do the insert for today, or for this video, and then the next video you'll get the linked list traversals where we'll actually print. Now the goal of a binary tree is so that as you're inserting items dynamically one at a time like a linked list, you're actually sorting the information as you insert it. That is where binary trees make up for the efficiency and the speed and the ability to have just one more piece of data or on-call or on-demand dynamic memory. So essentially what ends up happening is the way Google uses it is they send out their crawlers and they build all these binary trees from the information that they have, and as they're inserting information into the binary tree, that is all processing. So binary trees need quite a bit of pre-processing. But once you have the data in the tree and you need more data, the only thing you have to manage is balancing your trees again and making sure that they are as balanced as possible. And what I mean by balanced is that when you insert items into a binary tree, you're going to be looking at data, the data itself, and deciding which direction or how it's going to be sorted as you insert that data into the binary tree. So let's kind of get into the code itself, and I'm going to zoom in, and we're going to start with just the insert node helper and the insert function. So let's go ahead and go back to main, and what we're going to do is we're going to do integers first, and then we'll do customers. We'll put some customers in there. Okay, that'll be part of the when we put customers in, we will that'll be part of the second video. Okay. Okay, so we're going to instantiate the binary tree, and it's templated, so we're going to tell it to store integers. And then we're going to run this insert node function. Okay, so I'm going to say I want a BTree called myTree. And it's okay to put that on the stack. Did I call it BTree? Oh, I didn't put the template in it. Because just the pointers will be on the stack. Okay. So this is when we start adding things. Now, what I want to add is I want to add numbers that are not in order. You cannot insert numbers or values in order to a binary tree. And the reason being for that is because of the mechanism of how a binary tree works. The better or the more different your values are, the better your tree is. So I'm going to show you an unbalanced tree, and then, well, no, let's show you a balanced tree first, and then give you an idea of what a unbalanced tree does. So here is, we're going to do myTree.insert, and we're going to do the number 10 here. Okay, so that we're going to do first, and then we're going to continue on with this insert, and I'm gonna actually run this in the debugger, and I'm going to go back and forth between the debugger and the board, my little graphics tablet, and hopefully you'll be able to visualize kind of how a binary tree works. So I'm going to take another quick short break, and then we'll get started. Okay, let's get started. Now this is a whiteboard. Ignore these boxes and this box. I'm going to be using them as I go through the discussion. But when the binary tree first starts out, basically when we instantiate the binary tree, and I'm going to get rid of this guy just so, okay, we're fine. So when we instantiate this binary tree here, and we do a step into, what we find is that the root node is created, and the constructor is automatically called by assigning root to 0. So this is just your normal node pointer. It's not the node. So remember, this is just the pointer to the node, or is going to be a pointer to a node that exists on the heap. So this actually goes on the stack. The pointer itself. And when we assign the pointer to 0, we're basically just initializing it to null or nothing. And so the root node is created on the stack, and remember, it has its own address, and it's going to store the address of a node that it points to that we have not created yet. So that's going to happen when we do our first insert. we're also going to have a special node called current that's going to be used through each recursive call. We're going to create this current node when it becomes time. So let's go ahead and follow through the first insert. So far, the only thing that we have when the node is instantiated pretty much is a root that's pointing nowhere. So it's got 0 in here for what it stores. Okay, so let's go ahead and go back, and what we're going to do is we're going to go to main, and we're going to set a breakpoint here, and we're going to follow through on this insert code and see what happens. Okay, well, guess what? I got to go on pause again. Well, maybe it might be something simple. Nope, I'll pause and come back and let you know kind of what's going on. But it's kind of interesting that this guy would die on me, since this code has pretty much already been... Oh, really? Yeah, it is something simple. Forgot to do that. I must have erased it. Okay, so that's the fix for that error, if and when you come up to it. Maybe I did that wrong. That might be it. Okay, yeah, no, I'm going on pause. So we will, yeah, it was how I thought it was going to be. Okay, I'll be right back. All right, yeah, so I evidently not enough coffee, excuse me. B node. B node, that was simple. Not node. All right, let's see what we got now. Let me try our first insert. We still got problems. I think, oh, of course. So my fix caused another problem, which is usually why the guess and check doesn't work. Okay, I'll come back for the next fix. Well, of course, you got to change your constructors and everything that refers to node. You change to B node. So that's the next fix. I should have got that right before. Okay. So hopefully we got this fully ported, the node class fully ported to the binary tree class. There's no nodes in here. We've made them all B nodes. Let's cross the fingers. Getting closer. Okay. Another fix. This should be an integer returning main, as proper standard C++. And this is an error because I have, I'm trying to track down the error that I have in the binary tree library here. So usually what I do is when I'm having this kind of problem, I just comment everything out and I go from there. And I just bring back things a little bit at a time. Pretty good little editing error or, trick to fixing compiling errors. So I'm going to go ahead and bring this BTree back and see what's wrong with that. So I think some of that error issue is from the binary tree code. I think I didn't port something as I should have. So let's look at these insert node functions. I think it's probably oh yeah, look at that node root. That should be B node. Okay, we're getting better. We're getting there. Another node. That should be B node. New B node. Okay. Yeah, that comment all out trick is something I'm pretty sure you know all about. So now we can bring everything back, and we should have something that'll work. Getting closer. Okay, so something here. All right, I'm gonna pause again. Hopefully this is the last time. Nope, I missed some more B nodes. B node. B node. This is in my node class. Typical issue. Search and replace is okay, but you know, often I cause more problems when I do that. Okay, so no more node issues here. Okay, pause again, continue to fix. Okay, so I think I'm at the last fix here, and I should have known better. Of course, I probably need to put these guys over here, and I'm pretty sure that's gonna give us our last bit. So we're gonna uncomment and see where we're at now. Hopefully we got it ready to go and ready to be tested. Let's see. Okay, just a few little changes to make it right. And I'm going to zoom in on this and just give you some time, and let's make sure it compiles. Okay, so we got this part, and we'll scroll down. Got this part. Got this part. Got our binary tree with the insert function. Okay, so you got a couple frames of that. And of course, as you're following through, you should have it done too. But that's all the fixes. So we're ready to test and do a step into. So I believe we can uncomment these guys. All right. Not quite there yet. Okay. Okay, looks like the next error in our porting of the code that we grabbed, we have this statement right here where we're creating a binary node, but we must pass in the data that we're storing. In fact, we've been calling it data, so I'm gonna call it data, not storage. We've been calling it data. So what I got to do is I've got to overload the constructor for the binary node to allow us to pass in the data on instantiation of the BTree node. So I think I just need to rename this all to data. Keep with the naming convention that we've been working with this whole quarter. Okay, so those are done. And then I just need to go up to the binary tree and implement a overloaded constructor and pass in the data as a pass through. So of course I just got the default here. So we're going to take this and we're going to copy it and paste it. And here we go. We need a B node. And is it a pointer that we're passing? No, it's just the data. No, we don't need a B node. We just need, yeah, we do, because what's the data? No, we need a T for data. T for data. Okay, and then we're going to differentiate in this data, and now instead of assigning it to itself, which is what that little T thing is, kind of ridiculous, but it's the way they get over the non-assignment error from the compiler. So we're going to actually put it to equal to the data we pass in. So now we've overloaded the constructor to accept data as a pass-through. So that should fix that error that we have here, right here. Okay, and then just get the last little bits of storage identifiers. This is going to be data. and this is going to be data. Okay. All right, now we're ready to have some fun. Oh my goodness, I misspoke. Well, guess what? We may have to be doing video part 1 and video part 2 and video part 3. Let's see where we got there here. Get storage is not a matter. Oh, okay, we got to make this, we got to port this to our get functions. So it's not going to be get storage, it's going to be get data, set data. Good, of course. So storage becomes data again. And I just want to use the same naming conventions. Okay, that one wasn't too bad. Hopefully we can get to it sometime too. Cannot access left. Okay, so now this is an issue. Now the reason why this is an issue is because we are actually using private members, and for this one I'm gonna actually open this up public. And yes, it's a no-no, but it really is easier for you to understand when we're not using with, not doing it with accessors. So this is the only time where you can break the rules. And this becomes now, all this stuff becomes public. The left and right becomes public. You know what? Maybe we should build it so that we use the accessors. I haven't done it for a long time. Set left, set right. I just don't, it's just, now we're going to go ahead and do it easier. And then what you can do is once you get it working as public, then what you do is you get it working with your get and set. Okay. So maybe we'll do that at the end of the video, but it's just easier to discuss it without the accessors. Okay, that's our last kick. Okay, now we can have some fun. And guess what? I got to take another break after all that debugging. And what are we moving on? An hour? Okay, well, part 2 is coming. Okay, so this is going to be the porting and error, porting and, well, basically just call it porting the binary tree code into our code. So creating the binary tree. All right, so now I'm gonna go ahead and do another video that will continue on from this, where I will be inserting in nodes and walking you through the algorithm. But this is creating the binary tree. So I'm gonna go ahead and stop this and post it and get started on the next video.